Chapter 17 covers the atmosphere and the ways in which humans interact with it. At this point in class, we have covered the layers of the atmosphere. We have the troposphere at the bottom. This is the part of the atmosphere you are most familiar with because you live in it, you breathe it. Most of the weather you know as weather and the greenhouse effect both occur here. 80% of the mass of the atmosphere is found in the troposphere. Next, we have the stratosphere. This is the layer in which the protective ozone layer is located. Remember, this layer is like a natural sunscreen for Earth. The ozone molecules help absorb about 95% of the harmful UV radiation before it hits the Earth's surface. That's not all, but 95%. The UV filtering effect of ozone in the lower stratosphere allows us and other forms of life to exist on land and helps to protect us from sunburn, skin and eye cancers, cataracts, and damage to our immune systems. It also prevents much of the oxygen in the troposphere from being converted to photochemical ozone. The next two layers are the mesosphere and the thermosphere. We don't talk about them much because humans have little interaction with them. If you refer back to the graph we completed in class, it actually looks a lot like the one I have posted on this slide. Then you will remember air pollution is defined as the presence of chemicals in the atmosphere in concentrations high enough to harm organisms, ecosystems, or man-made materials, or to alter the climate. Remember, natural sources of gases in the atmosphere can be considered pollution as well if they are found in high enough concentrations. Natural sources of air pollution include wind-blown dust and other suspended particles, pollutants from wildfires and volcanic eruptions, and volatile organic chemicals released by some plants. We'll discuss these in more detail in the chapter. Human sources of air pollution mainly fall back on the burning of fossil fuels. All of these pollutants are semi-removed by natural processes such as the biogeochemical cycles, precipitation, and gravity. But even with the help of new technology that can remove these pollutants from waste before it leaves a motor vehicle or factory, the amount of pollution we emit into the atmosphere is too much for the Earth to take care of on its own. This is important to remember yet again. Prevention is better than cleaning up a mess later. Pollutants themselves can be broken up into further groups based off of mobility and reactivity. Mobile sources include things such as motor vehicles, and stationary sources include power plants and factories, aka things that are not moving around. Reactivity is a major concern with certain pollutants. If a chemical is emitted into the air and on its own it is found in a concentration high enough to cause harm, then it is considered to be a primary pollutant. If the chemical reacts with something else in the atmosphere to cause harm, then it is a secondary pollutant. Examples of secondary pollutants include carbon monoxide, carbon dioxide, nitric oxide, nitrogen dioxide, and sulfur dioxide. While there are many different chemicals that pollute our air, the EPA has established a list of 6 criteria pollutants. These chemicals make up the largest portion of the air pollution we face. These include carbon monoxide, nitrogen oxides, sulfur dioxide, ozone, lead, and particulate matter. We discussed quite a few different pollutants in class, but if you forgot most of them, at least focused on these 6. Carbon oxides, such as carbon dioxide and carbon monoxide, are formed during the incomplete combustion of carbon-containing materials such as fossil fuels. Sources of these pollutants include motor vehicle exhaust, the burning of forest and grasslands, smokestacks of fossil fuel burning power plants and industries, tobacco smoke, and open fires. Carbon monoxide affects the hemoglobin in blood, causing the transport of oxygen to body cells and tissues to cease. It can lead to heart conditions and irritated lungs. Acute exposure leads to headache, dizziness, and confusion. Nitrogen oxides form when nitrogen and oxygen gas in the air react under high combustion temperatures in automobile engines and coal-burning power plants. In the air, nitrogen oxides can lead to photochemical smog and acid deposition, both of which I will explain further shortly. Nitrogen dioxide can irritate lungs, impair plant growth, and decrease visibility in the air. Sulfur dioxide smells really bad. It smells like rotting eggs. About a third of the sulfur dioxide in the atmosphere comes from natural sources like volcanoes. The other 2/3 come from human activities, including the combustion of sulfur-containing coal in power plants and oil refining. In the air, sulfur dioxide is converted into aerosols because water molecules tend to bind to it to create suspended sulfuric acid. These aerosols eventually lead to acid deposition. Ground-level ozone is considered the bad ozone, unlike the good ozone found in the stratosphere. At ground level, this ozone can cause photochemical smog, irritate lungs, impair the immune system, and irritate the eyes, nose, and throat. Lead does not break down in the environment. It is a neurotoxin. It makes its way into the air by the use of leaded gasoline and lead-based paints, both of which have been banned in the United States since the 70s. The problem here is that the damage has already been done, and there are still houses that were built/painted prior to the ban that help lead to more air pollution today. Suspended particulate matter, or SPM, are the solid particles and liquid droplets small enough to be suspended in the air for long periods of time. When we viewed our slides under the microscope this week, we saw what these particles look like. There are two major classifications of particulate matter, PM10 and PM2.5. This refers to their sizes, about 10 micrometers and 2.5 micrometers respectively. These particles can include dust, sea salt, and bacteria. The biggest problem with particulate matter is the fact that it aggravates the lungs and airways. Smog occurs when the air quality is so impure that visibility is impaired. There are two major types of smog that are determined by the chemicals found in the air. Since the onset of the Industrial Revolution, cities have suffered a type of smog known as industrial smog, or gray smog. This consists mostly of sulfur dioxide, sulfuric acid, and particulate matter in the air, and occurs in areas where oil and coal are burned for energy purposes. The killer smog of 1952 in London occurred when weather conditions trapped emissions from the coal used to fire the city's industries and heat people's homes. Sulfur dioxide and particulate matter caused most of the 4,000 to 12,000 deaths, which led many industrialized governments to set stricter regulations on the coal industry. Photochemical smog forms when sunlight drives chemical reactions between primary pollutants and normal atmospheric compounds, producing a mix of over 100 different chemicals, tropospheric ozone being the most abundant. Because it also includes nitrogen dioxide, photochemical smog generally appears as a brownish haze. The amount of air pollution found in a given area is dependent upon a few factors. Factors that naturally decrease air pollution are precipitation and wind. Wind can move air pollution to a new location, and precipitation helps bring the air pollution out of the atmosphere, neither of which can truly be relied on as a means of removal because these just relocate the pollution instead of truly removing it. Obviously, urban areas tend to have more air pollution, but there are natural factors that can determine how much air pollution an area has, such as high temperatures and elevation. As we learned with the last slide, the higher the temperature, the higher the increase of these rates. Urban areas are what we call heat islands. They are small areas of heated air that are surrounded by much cooler rural areas. This is because there is a lot of human activity occurring in urban areas that increases the temperature in the area, such as the burning of fossil fuels and laying down dark-colored asphalt. These heat islands can naturally cool off as the air dissipates to the surrounding areas if it isn't too large and is found in a relatively flat area. Sometimes, cities can trap heat in a situation known as a temperature inversion. During a temperature inversion, not only is the heat produced by the city trapped in, but since there is no airflow or convection, any pollutants in the city will stay stagnant and be found in high concentrations in the air. Temperature inversions occur when cool air stays in place below a warmer air mass. Since the cooler air is already underneath the warmer air, there is no convection. There are two major types of temperature inversions, subsidence and radiation. In a subsidence temperature inversion, a city is located in a valley-like area over which a warm air mass flows and traps the cooler air mass underneath. These inversions may last for days until the air mass moves out of the area. On the other hand, radiation temperature inversions occur and wear off very quickly. Typically, the air near the ground cools off very quickly once the sun goes down. The air higher up does not. This warmer air is warmed even further when the sun comes up, but so is the air near the surface. As a result, radiation temperature inversions wear off rather quickly. Both situations can create conditions that are extremely tough on human health. Another major concern with pollutants in the air is acid deposition. Pollutants such as nitrogen and sulfur oxides combine with water vapor in the atmosphere to create clouds. They act as condensation nuclei. The water vapor actually attaches to the pollutant molecules as it condenses. This creates nitric acid vapor, sulfuric acid vapor, and acid-forming sulfate and nitrate salts. The two forms of vapor are wet deposition and will fall down in the form of snow or rain. The salts act as a particulate pollutant and can fall and pollute waterways and soil as well. In order for deposition to be considered acidic, it must have a pH of 5.6 or lower. Health concerns associated with acid deposition include respiratory diseases, but most of the effects are indirect. Acid deposition affects everything in the environment in which it falls. Acid precipitation has a tendency to bind to toxic metal naturally found in soil and leach into nearby waterways, and also from pipes into drinking water. This is actually the reason we have switched from using lead and copper pipes to less toxic materials. Any structures made of sedimentary rock, such as sandstone or limestone, disintegrates with acid deposition. This is because the rock itself is not cemented enough to hold its own against chemical agents such as this. When the acid makes its way to waterways, it drastically impacts the ecosystem by harming all of the organisms found there that don't adapt well to pH changes. This can drastically impact us financially by hitting aquacultures, forest, and agricultural areas. In aquatic ecosystems, the acid has a tendency to break down the mucus lining of fish and pulls out harmful metals from the soil that bioaccumulate and biomagnify in these organisms. If the pH change does not fall in the range of tolerance for any given organism, it will die. If the change in pH is too drastic too quickly, like we see with melting acid snow, then organisms will go into acid shock. In terrestrial ecosystems, the waxy coating or cuticle found on plants breaks down with acid deposition. Not only do metals leach into the soil, but nutrients are broken down or pulled out as well. Again, it impacts every aspect of the ecosystem. Here is a quick AP tip. If you are writing that something is damaging to ecosystems on an FRQ, be sure to be specific. In this case, just saying that acid deposition is bad because it hurts ecosystem won't get you any points. It's very vague. You have to be more specific and say, for example, that acid deposition dissolves the mucus lining of fish, which negatively impacts all of the organisms that interact with that species of fish. That's how you get all of those points. Let's take it back inside and look at indoor air pollutants. There are 11 common air pollutants that are found at doses much higher indoors than outdoors. While these pollutants can be found outside as well, their prevalence in such high numbers indoors is the reason they are characterized as indoor pollutants. The top most dangerous of these pollutants are cigarette smoke, formaldehyde, and radioactive radon-222 gas. Radon is a radioactive gas found in geographical areas with high levels of uranium deposits. As uranium decays, it breaks down into radon-222. This gas can lead to lung irritation and even lung cancer over the course of a human lifetime. It's actually the second leading cause of lung cancer in the United States after smoking tobacco. Your respiratory system can help protect you against air pollutants. It's the reason you have nose hair, mucus, and why you sneeze or cough. These natural barriers are broken down over time by exposure to air pollutants and only break down faster if you add smoking into the mix. You can reduce your risk by having your house tested and monitored for radon leaks on a regular basis. All of these indoor air pollutants lead to a situation known as sick building syndrome. Here, those affected can have flu-like symptoms, dizziness, headaches, coughing, sneezing, nausea, burning eyes, and chronic fatigue that are all related to the chemicals found in the air. Newer buildings have seen an increase in the likelihood of being quote-unquote sick because of reduced air exchange in order to save money and energy, as well as new chemicals that are released by carpets and flooring. All of the treatments for those floors, as well as all the cleaners you use in your house, just add to this effect. The United States has tried their best to create and enforce stricter air pollution laws. The most famous of these laws is the Clean Air Act, along with its amendments. The Clean Air Act was created in 1970 after there were many instances of killer smogs and temperature inversions. In the beginning, the EPA established the National Ambient Air Quality Standards to control the criteria air pollutants. Remember, those are lead, carbon oxides, nitrogen oxides, sulfur oxides, particulate matter, and ozone. These standards start at risk management, or looking at the potential harm they can cause, and move towards the levels of these pollutants, which are considered the maximum permissible levels for humans. Of these standards, we have primary and secondary standards. Primary standards focus on human health effects of these pollutants, and secondary standards focus on the environmental health and impact. As with all laws we have studied thus far, there are downsides. The policies still focus more on cleanup rather than prevention like they should, and focus only on a few pollutants instead of air pollution as a whole. However, the Clean Air Act has done wonders for reducing the emissions of the 6 criteria air pollutants, so we can't say that it has been ineffective. In 1990, the EPA added the emissions trading policy. This allows companies to trade their emission allowance for one pollutant with another company for a pollutant they desire more. It creates a fair system in which companies can buy and trade their pollution rights. These pollutants traded include sulfur dioxide, which, as we just learned, adds to acid deposition concerns. In 1997, there was a larger focus on the reduction of tropospheric ozone because of its role in photochemical smogs. We talk about reduction as the number one answer for pollution in this class, so I'll end on this note. We can reduce the amount of outdoor air pollution we create by reassessing our fossil fuel use. Fossil fuels add to most of our air pollution emissions. We can reduce our impact by taking sulfur out of coal or using low sulfur coal, converting coal to a liquid or gaseous fuel, and shifting to less polluting fuels, such as renewable resources. As for cleanup measures, we have implemented the use of smokestacks that emit the pollutants we create above their thermal inversion line to help prevent the high pollution concentrations we see with them. Remove pollutants after combustion through the use of scrubbers and smokestacks, and tax pollution generation to promote more sustainable usage of products and materials. Indoor air pollutants are a little different. The biggest concern here is looking at the air we have circulating through a building. Increasing circulation through a filtration system is important for indoor air health. Obviously, not smoking in a home can reduce your air pollution. At the industrial level, we need to start looking at the chemicals that are used in homes and seeing if we can switch to less harmful materials to help reduce our health effects associated with indoor air pollution. As for cleanup, ensuring the ventilation systems in buildings are up to date and any leaks are repaired is key. The more circulation through a building, the better. If you can circulate that air through a greenhouse, then you can reduce the amount of pollutants in the air naturally. Last, using more efficient chimney systems and exhaust hoods prevents pollutant buildup during cooking, namely carbon monoxide here. Thank you for listening, and don't forget to make your discussion post.